Hey everybody, Dr. A here, and in this video we're going to be providing some background information on how to analyze two-dimensional vectors using rectangular components. So let's go ahead and get started. We're going to begin by just describing how this works in terms of rectangular components. So basically, when we want to add or subtract vectors, generally, it's going to be more convenient to work in these things called rectangular components, which deals with resolving vectors into two components acting along perpendicular axes. Now, what are these two sets of axes that are perpendicular to each other? Well, usually that's going to be the Cartesian x and y axes. So the x being the horizontal axis, y being the vertical axis, okay? Now, what's great about this and the big advantage of using the standard Cartesian x and y axes is that we can perform these kind of analyses and calculations using basic right triangle trigonometry. So by working with rectangular components when analyzing and working with two-dimensional vectors, we can usually avoid using other things like law of sines and law of cosines. We can usually avoid having to draw a force parallelogram like we saw in our other videos, okay? Now, this is particularly useful when we have more than two vectors that we're adding or subtracting, okay? So if you watch the previous couple of videos, we talked about, if we've got two vectors that we want to add together and find the resultant, you can use this thing called a force parallelogram or a vector parallelogram, vector triangle, and use law of sines and cosines. But if you have more than two vectors, if you have 3, 4, 5, 6 vectors you want to add together or subtract from each other, then working with force parallelograms or vector parallelograms and triangles can be quite tedious because you're going to be applying a law of sines and law of cosines over and over again. So that's the beauty of rectangular components. It's a lot more efficient and user-friendly, okay? So how does it work? Well, let's go ahead and sketch a set of axes. Let's say we have the y-axis and the x-axis, okay? Now, let's say that you have this vector, all right? And let's say that, we call it vector F because, in statics, we deal with forces. So we have vector F here, okay? And let's say that we have a reference angle from the positive x-axis, theta, and let's say that we have another reference angle that we could utilize from the positive y-axis, phi, okay? So phi is the angle between the positive y-axis and the vector, and then theta is the angle between the positive x-axis and that same vector. So of course, we know that phi plus theta is 90 degrees if we're within one particular quadrant, okay? And so what can we write? We can say the following. We can say since the sine of theta is equal to f sub y over the magnitude of F, then we can say the y component of that force is the magnitude of F times the sine of theta. Now, where did I come up with that? How did I come up with this first relationship? Sine of theta is Fy over mag F. Well, we did it by looking at this as a right triangle, okay? So it turns out that you can resolve this force, okay, which is basically the hypotenuse of this sketched right triangle. Okay, you can resolve this into an x component, all right, which I'm going to call this fx, and a y component, which I'm going to call this fy. And so what I did here was I said the sine of theta is equal to opposite over hypotenuse. Well, what is that? Hypotenuse, well, that's just the magnitude of f. So the physical length of this vector is the magnitude of vector f, okay? So I used basic right triangle trigonometry, did a little rearranging, and I got fy is magnitude f times the sine of that reference angle theta. Now, similarly, we can say cosine of theta is adjacent over hypotenuse, which would be fx over magnitude of x. And so we can get that component, that x component fx, that's the one that's down here, right? That's this horizontal component, is equal to magnitude f times cosine theta. So if I were to sketch this back on my figure, this would be fx and this would be fy, okay? Now, you could also sketch that fy along the y-axis. You could sketch it over here as well. Now, why is that important to me? Why am I pointing that out? Well, you don't only have to use theta from the positive x-axis. You can use phi, that's a reference angle off the positive y-axis, right? So, similarly, what we could do is we could say, I'm going to say also, the y component could be written as the magnitude of f times the cosine of phi, and the x component could be written as the magnitude of f times the sine of phi. So notice that the trig operators are complementary to each other, and the angles are complementary to each other, right? Makes sense, right? Phi and theta are complementary angles. So how did I piece this together? Well, again, I said, for example, on the y component, I said the cosine of phi is equal to adjacent over hypotenuse. And I looked at this top right triangle, okay? Where's the right angle on that top right triangle? That's right here. So one more time, I said cosine of phi is equal to adjacent, which now is fy, divided by the hypotenuse, which is the magnitude of f. And then similarly, I said the sine of phi is the opposite side, right, which is fx, divided by the hypotenuse. And so I was able to rearrange and solve for fx here. So the moral of the story is what? The moral of this is be mindful where a reference angle is measured from, okay? Be very careful. If you flip-flop your sine and cosine recklessly, you're going to get the wrong answer, okay? So back to something I said earlier. What does this mean for adding multiple vectors together? So let's say if we have multiple vectors we want to add to determine a resultant, what we can do is we can resolve each vector into its x and y components, okay? And then what we do is we add all x components and add all y components. And so how can we say this mathematically? Well, we can say the x component of the resultant force, I'm going to call this FRX, is equal to the sum of all of the x components, the summation of f of x. And similarly, we can say that FRY, the y component of the resultant force, is equal to the sum of all of the individual y components of all those vectors you're trying to add together. And then finally, we can get the magnitude of the resultant force of multiple vectors that you want to add together. So let's write this down. The magnitude of this resultant force, F sub r, is computed as the Pythagorean theorem. So we would say magnitude f sub r is equal to the square root of frx squared plus fry squared. Okay, that's the Pythagorean theorem, right? Now, what if we want the direction of that resultant force, F sub r? Okay, so how do we get that? We're going to say the direction of F sub r can be computed as theta sub r equals the arc tangent of the absolute value of fry over frx referenced from a horizontal or x axis. Okay, now when we get to some examples, we're going to explore this in a little bit more detail and show some different variations of how we can handle this. Okay, but that's it in a nutshell. Okay, now again, this video is for the purposes of teaching statics, right? You may have learned this already in a physics course, or if you're currently in a physics course, this can help you have a better understanding of this topic at the Physics 1 level, all right? So let's continue with talking about some other aspects of this. There are, when doing this kind of analysis with rectangular components, we have two common notation methods whenever we want to do a rectangular analysis process, okay? The first is called scalar notation, okay? Scalar notation. How does this work? Well, what we do here is we algebraically add vector components as scalars, okay? And we want to keep track of the algebraic signs, okay? That's pretty easy. In fact, most of the time when I'm doing a two-dimensional vector analysis, I use scalar notation, okay? What about the other common notation method? Well, the second one is called Cartesian vector notation. Okay, Cartesian vector notation. So what we do is we perform similar algebraic operations as scalar notation. Okay, but what we do is we express the vector components in terms of unit vectors. Okay, in terms of unit vectors. Now, there are three common unit vectors that you may have seen in a math course or in a physics course, okay? We have the unit vector I, which is 1, 0, and J, which is 0, 1, okay? Now, that's for 2 dimensions, okay? For 2D. If you have a 3-dimensional vector, then you'll have I is 1, 0, 0, J is 0, 1, 0, and K is 0, 0, 1. And we'll put a note here for 3D, okay? And so how would this work? Well, again, you still decompose all of the vectors that you're trying to add together into x and y components. You add up the x components, you add up the y components, but then you express the resultant as this thing called a Cartesian vector using these unit vectors. So let's look at an illustration, okay? So I'm going to say, let's say we want to compute the resultant force of a vector F1 plus a vector F2, okay? And again, we're illustrating Cartesian notation right now, okay? So let's say we have this XY coordinate axes, and let's say that, I've got vector F1 here at an orientation theta 1, and let's say that I've got a vector F2 here at a theta 2, okay? And so vector F1 as a Cartesian vector would be equal to F1x times I plus F1y times j. So I'm expressing this F1 as what's called a Cartesian vector, and I'm incorporating these two unit vectors in here, okay? Now, similarly, we're going to have F2 expressed as negative F2x times I plus F2y times j. Now, where did this negative come from? Well, this is where you have to be really careful. Notice F2 is pointing into quadrant 2, okay? Which means it has a negative x component, all right? So if I were to kind of expand this out, look at F1 first. F1 has a positive x component and a positive y component. But F2 has a negative x component, and it still has a positive y component. So this negative indicates that F2 has a negative x component, which means it's pointing to the left, all right? Now, if I want the resultant here, if I want FR as a Cartesian vector, what I'm going to do is I'm going to add up the x components and then separately add up the y components, and I'm going to express it like this. F1x minus F2x times I plus F1y plus F2y times j, all right? And so what do these combined terms mean? Well, F1x minus F2x, that's just FRx. And F1y plus F2y, that's FRy, okay? And so, so what do we do from there? Well, after this, you can use any of the right triangle trigonometry to get all the components. You can use the arctangent function to get the direction of the resultant force. Everything else is pretty much the same as with scalar notation, okay? So at this point, I'll make a note, all right triangle trig operations are valid, okay? And another note I'm going to make is Cartesian notation is very convenient when dealing with 3D vectors. Okay, now I said it earlier in this video, you can use Cartesian vector notation with these unit vectors for two-dimensional vectors, no problem. I mean, we're doing it right now, right? However, I did mention earlier, most of the time when I'm dealing with 2D vectors, I just use scalar notation, okay? It's a bit more convenient, and it's a little bit less tedious to keep up with things. But when you're dealing with three-dimensional vectors, which we do talk about that in statics quite a bit, the Cartesian vector notation tends to be better for 3D vectors, okay? It makes those calculations a bit more convenient and easy to deal with, okay? Let's talk about the sign convention real quick, and then we're going to wrap up this background video. So sign convention, okay? So typically we take vectors pointing to the right as positive and vectors pointing up as positive, okay? So whenever you have a component pointing to the right, we'll take that positive, and if we have a y component pointing up, we take that positive. So again, algebraically, if you have a vector pointing into quadrant 2, like we saw here, then you're going to have a negative x component and a positive y component. So here's a quiz for you. See if you can answer this question. If I have a vector pointing into quadrant 3, what are the signs, the SIGNs, the signs of each component pointing into quadrant 3? The x component is going to be negative and the y component will be negative, right? Both components negative. What if I have a vector pointing into quadrant 4? What are the components, positive and negative, or negative? So a vector pointing into quadrant 4 is going to have a positive x component, but a negative y component, all right? So these are things we need to remember from our knowledge of mathematics and physics, okay? So hopefully this video was helpful for you. If it was helpful for you, please hit like and subscribe and be on the lookout for other videos like this. Thanks for watching.